talking about nuclear fission. Now, before we get into the topic of nuclear fission, I would highly recommend that you make sure that you understand what happened in the last lesson, which was on mass energy equivalence and binding energy. If mass energy equivalence or binding energy is confusing to you, I would take a moment and kind of sit with that for a second, make sure that that makes sense to you before you jump into today's lesson on nuclear fission, because nuclear fission relies heavily on concepts about binding energy and mass energy equivalence. Today we'll talk about nuclear fission, and then in the next video we'll talk about nuclear fusion. When we talk about nuclear fission, we are talking about the kind of stuff that we use in nuclear power plants and nuclear reactors. We're also talking about the kind of stuff that we use to build an atomic bomb. So today you're going to learn a little bit about what an atomic bomb looks like and how to build one. But before we get into that, there's a little bit of background information that you need to know. Here's the first piece of background information. The first piece of background information is that not all elements have the same binding energy. Not all elements have the same binding energy. Some elements have more binding energy and other elements have less binding energy. And how much binding energy an element has depends on how hard it is to pull it apart. Now, this normally depends on a few factors. One of those factors is the stability of the nucleus. If you have a nucleus that is already very unstable, something like uranium or radon, something really, really big, well, that nucleus is very, very easy to pull apart because it's already about to fall apart anyway. And so something like uranium or radon or any of those really big elements, they are going to have a very low binding energy. This is in contrast with something that's smaller on the periodic table, something like titanium, which would have a much more stable nucleus and thus would have a much higher binding energy. So the first thing that matters is your size. If something is too big, then it's going to have a much lower binding energy than if it's a little bit smaller, because if it's way too big, it's already unstable. But that also goes the other way. If it's a really, really small nucleus, it's very easy to pull it apart because there just aren't that many protons and neutrons. So if you have a very small nucleus, something like helium, well, helium is only 2 protons and 2 neutrons. So it's very easy to pull apart helium. Helium has a really low binding energy. Here's what this means. If you were to think about binding energy, things that are really big atoms are going to have very low binding energy. Things that are very small atoms are going to have very low binding energy. And it's the stuff in the middle that's going to have really high binding energy. That's the first idea. The first idea, and I write this down somewhere, the first idea is that not all elements have the same binding energy. The ones on the ends, on the very big side of the periodic table, the really big elements have a really low binding energy. The really small elements have a really low binding energy. And the ones in the middle have a high binding energy. Before we move on, explain that to yourself. Make sure that you understand why do the atoms on the ends have low binding energy and the atoms in the middle of the periodic table have a higher binding energy. That's the first thing to understand. Not all elements have the same binding energy. Okay, after you understand that, here's the next move. The next move is to say that because not all elements have the same binding energy, the mass of a proton or a neutron, what we call a nucleon just means something that lives in the nucleus of the atom, like a proton or a neutron. The mass of a nucleon is not the same in every element. This means that the mass of a proton, we already know that the mass of a proton is way more when it's outside of a nucleus than when it's in a nucleus. But this also means that the mass of a proton is different for different nuclei. For example, the mass of a proton in carbon is not the same as the mass of a proton in iron. And it's also not the same as the mass of a proton in uranium. They all have different masses. And here's the key idea, and this is what you need to take away, and do write this down somewhere. That if something has a greater binding energy, if an element has a greater binding energy, the mass of the nucleons, the protons and the neutrons, is less. Because if you think about it, if you think about binding energy as how hard it is to pull that thing apart, To pull something off, to pull a proton out of a very, very stable nucleus, that's going to take a lot of energy, and so it's going to gain a lot of mass, which means when it joins up with its friends in the nucleus, it's going to lose a lot of mass. So, here's your idea, and do write this down somewhere because this is critical, is that if you have a higher binding energy, for a particular element, the nucleons, the protons and the neutrons, have less mass. The higher the binding energy, the less mass the protons and the neutrons inside of that atom have. Those are your two big ideas. And we're going to take those two big ideas and we're going to look at a little graph here. This graph, I'll put it up on the screen. This graph is the key to both nuclear fission and nuclear fusion. Before we can even talk about nuclear fission or nuclear fusion, you have to understand this graph. This graph is probably like the most important part of this whole video, is understanding the graph. So we're going to take a look at this graph here. This is a graph. Wait for it. It'll be here soon. Thank you for your patience. It's on its way. Okay, this is a graph of, you can see on the y-axis, this is the mass per nucleon, and on the x-axis is atomic number. I'm going to move this little guy up here. Okay, here's what I want you to see. I want you to see that here you have atomic number increasing this way, and here you have the mass per nucleon increasing this way. By mass per nucleon, we mean how big are the protons and the neutrons. Remember what we said, that not all elements have the same binding energy. The elements that are on the ends, the very small elements or the very big elements, those are the ones that have the lower binding energy. But it's the one in the middle that has the lesser binding energy, or that has greater binding energy. I gotta move this out of the way. Sorry, one second. We can do it. Okay, here's what I want you to see. The point at which you get the lowest binding energy, or sorry, the highest binding energy, is right here at iron. Iron is the perfect sized element. If it were too small, then it would be really easy to pull apart because there wouldn't be that much to pull apart. If it were too big, it would start to get unstable, but iron is just that perfect little guy right in the middle that's big enough to be hard to pull apart, but not so big that it becomes unstable. Iron is the tipping point. Here's what this graph shows you. This graph shows you that here you have mass per nucleon this way. As you go back from iron, getting smaller and smaller and smaller, those nuclei get easier and easier and easier to pull apart. Since they get easier and easier and easier to pull apart, the protons and the neutrons get more and more mass, because less binding energy means more mass. As you go towards iron, more binding energy means they have less mass. So elements that get closer and closer to iron have more mass, or have less mass in their protons and neutrons. Then, as the binding energy gets lower and lower and lower again as you progress towards uranium, and that binding energy is dropping, well then the mass of the protons and the neutrons is getting bigger because the atom is easier to pull apart. So over here you have protons and neutrons that have a little bit more mass from uranium than you do from something like any of these other elements down here that are on the other side of iron, like this. So here's the main idea. The main idea is that different elements have different sized protons depending on their binding energies. If you can understand this graph, then you'll be set to understand nuclear fission and nuclear fusion. Here's the idea. What if I could take a uranium-235 nucleus, which has protons and neutrons that are very big, and what if I could split that nucleus into smaller nuclei, like these guys right here? if I could take this nucleus and I could split it into smaller nuclei, when I split it, the atom would become more stable and the binding energy would increase, which means the mass of the protons and the neutrons would decrease. If I took something big like uranium-235 and I split it into smaller atoms, when I split it into smaller atoms, I'm saying this again because it's really, really critical. This is the whole idea behind nuclear fission. When I split it into smaller atoms, the protons and neutrons shrink. When they shrink, they release mass, and that mass comes out in the form of energy. The idea of nuclear fission is to use E equals mc squared to our advantage. If we can get protons and neutrons to lose mass, that means they're giving off a whole lot of energy. So the way that we do that is we take an atom where the protons and neutrons are very big, and we split it to make an atom where the protons and neutrons are a lot smaller. In nuclear fission, we progress on the graph this way. We take a very big element and we split it into smaller elements. Anytime you're going downhill on the graph, protons and neutrons are getting smaller. And if those protons and neutrons are getting smaller, they're releasing energy. That's the idea of nuclear fission, is to go this way on the graph. Nuclear fusion, quick preview for you, which we'll talk about in the next video, we go this way. Once again, shrinking down protons and neutrons by putting protons and neutrons together instead of taking protons and neutrons apart into a more stable atom. This is the idea on this side of the graph of nuclear fission. We take an element. I know I've said this like a gazillion times and I say it so slow and some of you are probably like, I already got it, Miss Wilson, I heard it, but I'm saying it one more time. We take an element that has really big protons and neutrons. We split it into two smaller elements that have smaller protons and neutrons. It loses mass in the form of energy, creates a good amount of energy. Let's go ahead and take a look at exactly what this would look like. Let me actually pause and get resituated real quick. Okay, here I've drawn a little illustration of what this process of nuclear fission looks like. The way that nuclear fission works is we start with an atom that's relatively unstable, typically uranium-235. This atom has to be unstable, and you want something really, really big where the protons and the neutrons are already really, really large, because we want to shrink those protons and neutrons down and get them to release energy. So we start with something like uranium. In uranium, the protons and the neutrons are very, very large because the atom is somewhat unstable. Then what we do is the idea is if we can get this really big atom to split into smaller atoms like krypton or barium, if we could get it to split into smaller atoms, then the protons and the neutrons would shrink and they would release mass, in the form of energy. Here's the idea. You take an atom like uranium. Now, it turns out that you can't just use any isotope of uranium. Uranium-238 is not what we call fissionable. So you have to use uranium-235 to get this job done. But you take some uranium-235 right here. Pretend that I drew 235 nucleons here, but obviously I did not. And what you do is you take a little neutron here. Here's our little neutron. And you slam a neutron into uranium-235 as hard as you possibly can. When you slam the neutron into uranium-235, this neutron will then break the nuclear strong force and start to separate these protons and neutrons apart. And what it does is after it separates them, you get two new atoms. One of them is going to be, whoa, that looks like an R, barium. And this barium, it's going to be barium-141, almost always that results, and it has atomic number 56. And then down here, you'll end up with another element, and this element that you'll end up with is krypton. And krypton has an atomic number of 36. So these two will split, and then you'll also get three little neutrons that go flying off. Here's a little neutron, here's a little neutron, here's a little neutron. Now, what happened was you took this uranium-235, which had very, very big protons and neutrons, you split it into barium and krypton, the protons and the neutrons shrank, and it released a whole lot of energy. This is nuclear fission. It's the process of splitting an atom so that the protons and neutrons shrink and release energy. A few things to notice here. Oh, we got an announcement.
Could you call the main office?
Awesome. A few things to notice here, or a few things to point out. First, did you know that the energy released in the fission of one uranium nucleus, it released in this process right here, is about 7 million times the energy released by the explosion of one TNT molecule? If you had to choose uranium-235 and splitting one of those in half, or splitting one TNT molecule in half, you should go with this one if you're looking for a big explosion. It would take 7 million TNT molecules to do what one little fission here does. That's because just a little bit of mass turns into a whole lot of energy. Another thing happens here. Do you see how it was a whole little neutron that went flying into a uranium-235 in order to start this process? Well, now I have 3 new little neutrons that are all zippy-zapping off in different directions. And if those little neutrons run into another uranium-235, they'll cause that uranium to split, and that will release 3 more neutrons. And then those 3 neutrons will go off and hit other uranium-235 atoms, and they will cause those ones to split. And then you get what we call a chain reaction, where each little uranium-235 breaking releases 3 new neutrons that then go and create nuclear fission for 3 more uranium-235s. And you can see how this would multiply so that the explosion would get bigger and bigger and bigger and bigger. This is what we call a chain reaction, and in some ways it can be helpful, and in other ways it can be unhelpful if it gets dangerous. Before we look at how we take care of chain reactions, let's do a little bit of practice problem. Could we figure out exactly how much energy is released by this reaction? Let's go ahead and try it. I'll pull up a new page here. Okay, here's a little practice problem. Let's see if we can figure out how much energy is being released in this reaction. We would start this problem by starting with a little transmutation equation. Here's what we started with. We start with some uranium-235. And that uranium-235 is going to be combined with a little neutron that goes running in. And together, they're going to create some krypton and some barium. Oh no, my R got lost. Some krypton and some barium. This is barium-141, and it has an atomic number of 56. This is krypton-92, and it has an atomic number of 36. And then lastly, we're going to release 3 little neutrons here. So we're going to be left with 3 little neutrons left over. Okay, if I wanted to calculate how much energy was being released by the fission of one little uranium nucleus, I would need to know a few things. I could do this very similarly to the way that I would do a binding energy problem, where I start by finding the mass defect, then I convert that mass defect into kilograms, then I find the binding energy, and I convert that binding energy into mega electron volts. Here's how I would do it. To start, I would need to know a few things. For example, I would probably want to know the mass of uranium-235. I would also want to know the mass of krypton-92. I need to know the mass of my barium-141. And I need to know the mass of a neutron. If I knew all of these masses, then I could find the mass defect. And if I could find the mass defect, well, then I could most certainly find the amount of energy. Here's how I would do it. First, actually, what I'm going to do is, for the sake of our time here, I'm not going to actually give you numbers here. I'm just going to kind of show you how to set up this problem, and then you could plug in numbers if you want to and solve. I'll show you what the numbers should be if you were to do this right, but I just really want to show you kind of how we set this up here. The first thing that we want to do is we want to find out how much mass we lose, because the amount of mass that we lose is going to be the amount of energy that gets released. So I'm going to start by looking for my mass defect. To find my mass defect, here's what I'm thinking. I'm going to do how much mass I started with minus how much mass I ended with, and that will give me the amount of mass that became energy. To do that, I'm going to do the mass of the reactants minus the mass of the products, because you'll agree that's how much I started with minus how much I ended with. Products, like this. The mass of my reactants here, well, I got a few masses going on. The first thing that I've got is I've got the mass of uranium-235. I also have the mass of a neutron here. And then finally, the mass of my products. I've got a lot of products. I have the mass of my krypton, 92. The mass of my barium, 141. And finally, I've got 3 neutrons, so I want the mass of all 3. So I'll take the mass of 1 neutron and I'll multiply it by 3. And that gives me my mass defect. So I could plug in numbers here, and you could plug in numbers if you knew all of these numbers, and you'd get a final answer. And the final answer that you would get would be something like 0.189. Whoops, nope, that's not true. 0.185. Oh, I'm going way too fast. Sorry, computer. 5, there we go, 9.61 atomic mass units. That's a 6, by the way. I know it doesn't look like it, but it is. Okay, fine, I'll fix it. 6. Oh, gosh. I did too much. You guys are like, wow, this is a lot just to write one number. Okay, so sorry about that. Then, from there, I would not be done, because I would want to find this mass in kilograms. So what I would do is I need to do a unit conversion. I would say that to find the mass in kilograms, I could take the mass in atomic mass units, and then in order to get it into kilograms, I'm going to do a little unit conversion here. I'm going to say that we all know that 1 atomic mass unit is worth 1.6605 times 10 to the negative 27th kilograms. Plug that into your calculator, and you would get that the mass defect is something like 3.08788 times, that's a 0.8788, times 10 to the negative 28th kilograms. Now we're not done, because I'm not really looking for the mass defect of this problem, but I'm actually looking for how much energy gets released. To find out how much energy gets released, I would then need to turn that mass into energy, and the equation that I use to do that is E equals mc squared. So I say that the amount of energy that gets released, delta E, is equal to my change in mass, the amount of mass that I lost, times c squared. Well, you could plug in here the amount of mass that you lost in kilograms, and you could plug in your c squared if you want to here, and I'm not going to plug in any numbers because I trust that you can do those things. And you would get something like 2.77909 times 10 to the negative 11th joules. But we're not done yet. Got to do one more unit conversion to get that thing into mega electron volts. To find this thing in mega electron volts, we would take this number, the energy in joules, divide by joules to get into electron volts. Hey, you know that 1 electron volt is equal to 1.602 times 10 to the negative 19th joules. But if I want it in mega electron volts, then I would go from electron volts to mega electron volts, and we know that 1 mega electron volt has 1 times 10 to the 6th electron volt inside. Plug that into your calculator, and then you'd get a nice final answer of 173.5-ish mega electron volts. And that would be your final answer. This amount of energy is a crazy amount of energy for one little uranium atom. This is why a lot of people would get very, very excited about the idea of harnessing this energy and harnessing the power of nuclear fission to like run our whole world, to create electricity for all the things that we use it for. So that is kind of the general idea. Now, that's how we calculate it, but let's look at what kinds of things we would do in order to either use nuclear fission to build an atomic bomb or to create a nuclear power plant. The first thing before we talk about atomic bombs or power plants is that you have to understand this concept that we call critical mass. Here is the idea of critical mass. If you saw in our little equation from before, what you see is that you have a neutron that interacts with a uranium atom. Then that uranium atom will split into two other atoms and 1, 2, 3 little neutrons, and those 3 little neutrons will go flying. Now, if those 3 neutrons run into 3 other uranium atoms, uranium-235 atoms, then they'll cause the uranium-235 atoms to split. And then that will cause 3 new little neutrons to go running out. 3 neutrons from each of the 3 uranium atoms. Then those neutrons will go and hit other uranium-235 atoms and cause them to split. And those will hit other uranium-235 atoms and cause them to split, because then you have more neutrons that are being released. And this is what we call a chain reaction. Now, a chain reaction will cause an explosion, but not all the time. A chain reaction will cause an explosion if it's making enough uranium-235 atoms split. But if it's not, then it won't create a explosion. The determiner of whether or not, one of the big determiners of whether or not we get an explosion is critical mass. Here's the idea. If you have a mass of a uranium that is very, very small, this was an atom, pretend this is like a bunch of atoms of uranium-235. If you send one little neutron into this uranium-235, well, it'll interact with one of those little uranium-235, and one of those little uranium-235s will send out new little neutrons, and those new little neutrons will go flying, and then those will interact with more uranium-235s, and that will create more neutrons, and those more neutrons will go flying. But hey, check it out. Once those neutrons go flying, a lot of them will actually make it out of the uranium-235 before they keep making uranium-235s split in half. And so what happens is, if you have a very small piece, well, most of the little neutrons will escape before they make any big explosions happen. But if you have a big piece of uranium-235, something like this, I don't know where the other half of my circle went there. It just kind of like disappeared. Something like this. Okay, fine. I'm just going to try it one more time. Sorry. Okay, try something like this. Why does it keep stopping halfway around? Okay, fine. We'll go with that. Say you send a little neutron into one of these little guys. Well, that little neutron will then hit a uranium-235, which will release 3 more neutrons. Check it out. These will then release 3 more neutrons when they hit more uranium-235. And then when those little neutrons hit more uranium-235, then they'll release more neutrons like this, and this, and this. And then this guy will release more neutrons when it hits a uranium-235. And then that uranium-235 will release more neutrons. And then those neutrons will go and hit more uranium-235 and release more neutrons, which will then go and hit more uranium-235. Hey, do you see how we have a lot of uranium-235 that these little guys are interacting with before they actually make it out of the chunk of uranium-235? That will cause a serious explosion. The difference between a little guy that won't create a big explosion and a big guy that will create a big explosion is what we call the critical mass. The critical mass is the tipping point between no explosion and big explosion. If you were to build an atomic bomb, you'd want to be above the critical mass. But if you're building a nuclear power plant, you'd want to be below the critical mass. Here's how you would create an atomic weapon. If you wanted to build an atomic bomb, what you would do is you would take 2 pieces of uranium-235 that are each below the critical mass. So say that I have one piece of uranium-235 here and another piece of uranium-235 here. By themselves, neither of these is quite explosive because it's not big enough to create an explosion. But what you'd do is you take one half and you'd put it over here, one half and you put it over here, and you'd put a little neutron here between them. Then on either side, you take some TNT. When you're ready for your bomb to explode, you'd explode your TNT on this side, explode your TNT on this side, and what that would do is it would shove these two halves together. Now, originally by themselves, they're below the critical mass, so they're not explosive, but if you shove them together, they are above the critical mass, and you shove them together on a little neutron, that neutron will interact with one of those uranium-235s, and it'll start a chain reaction, and you will get a very serious explosion. And that's the whole idea behind the nuclear bomb, was this. You just take two pieces of uranium-235 that are below the critical mass, shove them together, and you got a nuclear bomb. That's the idea. Now, this is not what you would want to do if you were creating a nuclear power plant, because if you're creating a nuclear power plant, you would not want an explosion. So in a nuclear power plant, what you would do is most of the time you would have pieces that were below the critical mass so that they're not actually going to explode. And you would also have some other safety features. Now, in a nuclear reactor, the whole idea of a nuclear reactor is to say, well, we could use this energy to actually fuel our world because one uranium fission puts out a whole lot of energy. As it turns out, 1 kilogram of uranium fuel yields more energy than 30 freight car loads of fossil fuels. With 1 kilogram of uranium, you can do more than 30 freight car loads of fossil fuels. You could understand how people would be very excited about this idea of using uranium in order to create energy to run our whole world. But there is the possibility and there is the nervousness of, wait a second though, if you are doing this, there are a few implications that are not good, and one of them is the safety implications. We do not want an atomic bomb in a power plant. We want something that's creating power that can be used to create electricity. We don't want something that is so explosive that, it's going to blow up our whole city and society. So that's not what we want. So here's what we do. We have a few safety things. The first thing that we do is we make sure that our uranium, our fuel, as we can call it, is mostly uranium-238. Uranium-238 is what we call not fissile, meaning it's not fissionable. Uranium-238 doesn't break down into pieces. Uranium-235 breaks down into pieces very, very well, but uranium-238 does not. So what we do is when we make our fuel for our nuclear reactors, we make them mostly uranium-238, which is not fissile, and when a little neutron hits it, it won't break into pieces. And then we only make about 3% of it. Did we get a percent sign here? Did I do my percent sign right? Why am I all of a sudden all crazy about percent signs? Yeah, that's totally right. Wow, that was weird in my brain. Only 3% of it is actually uranium-235. This prevents serious chain reactions because there's no possibility of a chain reaction if you only have 3% uranium-235. That puts you way below the critical mass, and so you're pretty much safe there. Another thing that we do is we also put control rods inside of our nuclear reactors. A control rod is basically what it sounds like. It's basically a rod that prevents chain reactions from happening. Control rods are mostly just rods that are made of cadmium or boron. And what they can do is cadmium and boron can both absorb neutrons very, very well without creating any kind of reaction. So what you do is if your reaction is getting pretty serious and pretty fast and you have a little bit of a chain reaction sort of situation going on more than what you want, then what you would do is you would drop a little bar of boron in there. The boron would absorb the neutrons and keep the reaction from continuing. Once it absorbs the neutrons, then there are no more neutrons to go and hit the rest of the uranium-235. So those things help make it a little bit safer. People who have issues with nuclear fission also bring up the point that, hey, you actually do have some environmental issues and some waste issues. In every uranium-235 reaction, you get byproducts of krypton-92 and barium-141. Now, naturally, krypton and barium are not that radioactive, but in this case, these isotopes are way neutron rich, which means that they will undergo beta decay. That means that your byproducts of this little reaction here are both radioactive. Not super awesome for the environment or for people. So what we do is we take those radioactive byproducts, we put them in lead containers, and we bury them in the ground. And that's the idea. So some people take issue with the fact that we are creating radioactive byproducts, and that is not super awesome. We don't have a great way right now to dispose of these radioactive byproducts in a way that's super safe. So that is definitely a downfall of nuclear power and nuclear power plants. However, a lot of people will argue, yes, we are making these radioactive byproducts, but if you think about it, nuclear fission is creating way more energy for way less. You think about the 30 freight cars of fossil fuels versus 1 kilogram of uranium. Even though you create some byproducts, you're not creating that many radioactive byproducts in comparison to how many fossil fuels you would have to burn. So that is a little bit of an issue. Another issue with it is that uranium-235 is actually very, very rare. And so it's very hard to find uranium-235, which means most of the time we end up making uranium-235, which is a whole other complicated process. So these are some of the pros and cons of why nuclear power could be super awesome, but also why some people have some hesitancies. Mostly because of safety issues and also because of the waste that we have and how we have to actually make uranium-235 to make this happen. However, it does produce a lot of energy for very little, which is why a lot of people think that nuclear power could really help us out a lot in protecting our environment and saving some of our fossil fuels. Those are some of the main ideas around nuclear fission. When you come back tomorrow, we will talk about nuclear fusion. But before then, can you please check and make sure that you understand these things first? Do you understand how that graph works? Because that graph is going to be essential to nuclear fusion. Second, can you figure out one of those mathy problems? Do you know how to do one of those? Third, do you understand the idea of critical mass? And fourth, what are some of the pros and cons of using nuclear reactions for power? And that is all we have for today, folks. Have a great and wonderful rest of your day, and I will see you next time. Bye, good people.